Today we will start the last module, that is plastic analysis. First you have to know what is elastic analysis and plastic analysis, what is elastic theory and plastic theory. So you know already what is elastic theory. The analysis of structure by elastic theory in which stress-strain relation is assumed to be linear. The design based on this theory assumes that the structure fails if the stress at any point reaches the yield stress. The service load is restricted to the values of that at the highly stressed point. The stress is equal to the working stress. The working stress is defined as the yield stress divided by the factor of safety. The designer has a concept that the structure would fail if the design load applied is equal to the factor of safety times the working load. But this is not the correct concept. Here you see, so this is the stress strain diagram for mile scale. So this is the A is the unit of proportionality, and B is the upper yield point, C is the lower yield point, and D is the ultimate stress point, E is breaking point. So here up to A, that is the stress is directly proportional to strain up to the limit of proportionality. Then coming to the point P, so this is the upper yield point. Then at the point P, suddenly the stress decreases and that reaches to the lower yield point. Then once again, so when the strain increases and the stress increases and it reaches at the ultimate point D, that is called the ultimate stress point. Then the stress is decreases and the breaking takes place at the point E. So here you see the stress strain curve is a linear between the origin and the elastic limit, which is very close to the yield point. After upper yield point, there is sudden drop in stress up to lower yield point. The designer normally treats the lower yield point at the limit of proportionality. Lower yield point to the ultimate stress point is the zone of strain hardening zone. This is called the strain hardening zone. From C to D, so this zone is called the strain hardening zone. At the ultimate stress point, the neck formation starts and the load carrying capacity reduces. Finally, the breaking takes place at the point E. So this is the breaking point of the stress strain curve. Let us take one simply supported beam. This is simply supported beam. This is the width and this is the depth of the beam. Consider the stress across the highly stressed section. So suppose if there is having the load, UDL load or point load. So where you will get the maximum bending moment? In the simply supported beam. So at the loading point or at the midpoint of the section. So you have to take where the bending moment is your maximum. So you will get the maximum stress at that section. At the highly stressed section of the simply supported beam with a gradually increasing load. So this is the stress diagram. This is your stress diagram. So the stress reaches F, that is your within the elastic limit. And when the load increases, the stress reaches the yield stress, Fy. Then here you see, this is the figure A, B, C, D. Here this is the stress. So this stress is here within elastic limit, and this is the stress at the yield point, and this is the stress after yielding the section. Here after yielding the outermost fiber, then the yielding that goes to inner side. And in figure D, so here the fully top fiber and the bottom fiber, the yielding takes place. So here you see, so within the elastic limit, the stress varies linearly across the section, and the maximum stress will get within the yield stress. Just at the yield stress, so you will get the maximum stress Fy. As the load increases, the extreme fiber will reaches the yield stress. So when the load increases, the extreme fiber, this is the extreme fiber. So this is the extreme fiber reaches the yield stress first. As shown in figure, extreme fiber reaches the yield stress as shown in figure 1b here. Fy. These fibers have a little capacity to resist load. Even if we neglect this additional capacity due to strain hardening, the section can still resist more load. if you neglect the strain hardening effect, still the section will resist the additional load, because the interior fibers are still under stress. When the yielding takes place at the outer fiber, the interior fibers is under stress, that will take the more load. So as the load is further increased, the outer fibers just expand or contract without resisting the load, but the inner fibers continue to resist the load. So when the load increases, so after yielding the outer fiber, when the load increases, so this yielding continue in the inner fiber without taking the more load, without resisting the load, till they also resist the without resisting load, but the inner fiber continue to resist the load till they also resist the load as shown in figure 1c. So here you see, so what is the load you are taking outer fiber, but the inner fiber is under stress, and when you will increase the load, the yielding of the inner fiber takes place. So it will take that more load without resisting load, but inner fiber continue to resist the load till they also resist the load as shown in figure 1c. This one. So the load carrying capacity increases when the inner fiber yielding takes place. The resistance to load continue till the entire section yield. Till the resistance to load carrying capacity is continue till the entire section is your yield. So here you see, so this is the yielding stress. After yielding the all section, this portion, the compression and the tension portion. So here this yield stress is remain here. This is the constant. So after yielding, this is the stress diagram. And the tension side also, this is your stress diagram. So first here you see, so this is your within elastic limit, what is the stress is your, this is your FO. And at the yielding stress, so this is the stress diagram. But here the external outer fiber is your yielding, but the interior fiber is your under stress. So when once again you will increase the load, the yielding, the resistance to load continues till the entire section yield. Thus, we find that a section can resist load even after the outer fiber yield. But in working stress method, so what you are taking, so you are considering the yield stress for any design, But this is actually, after all the fibers at a section yield, the section behaves like a hinge. For further load, it rotates freely without resisting additional moment. Now, thus we find that the section can resist load even after the outer fibers yield. So after yielding the outer fibers, the section resists the more load. Here, this resists the more load. Till all fibers yield are the section. So this is the stress diagram of various loading stage. So this is your before elastic limit. This is at the elastic limit at the yield point, and this is your after yielding, and this is your fully yielding at the section. So let us consider the load carrying capacity of a fixed beam. Let us take one fixed beam. At the bending moment is maximum at support. You know, in fixed beam, the bending moment is maximum at the support. So first extreme fibers are the support yields. In the case of fixed beam, so what will happen? So at the fixed end, first the yielding takes place, because here the bending moment is maximum and the stress is also here maximum. So the yielding takes place at the fixed end first. For further increase of load, the entire section at support yield. Even at this stage, the structure will not collapse. When yielding of the support takes place, in the case of fixed beam, so that case there is no collapse of the structure. Since a beam with two hinge at the, so what will happen? So the hinge formation takes place at the fixed end. So after yielding the total section, so what will happen? The hinge formation takes place at the fixed end. Hinges at the ends. And due to this hinge, the structure is also remain in the stable form. That is not the collapse of the structure takes place. For further load, it acts as simply supported beam. So further increasing the load, because this is the hinge formation takes place at the fixed end, and further increase of the load. So what will happen? The mid section, the yielding of the mid section takes place. And further load, it acts as simply supported beam till all fibers at mid section is your yield. You see, in the case of fixed beam, so the negative moment is your maximum at the support, fixed end, and the positive moment is your maximum at the midpoint. midpoint or under the loading. What will happen due to increase of load after yielding the all fibers at the fixed end, the hinge formation will start. Then if you will increase that further the load, here at the mid section the positive moment is your maximum. So the yielding takes place at the positive moment section. And after yielding this one, then the collapse of the structure takes place. But when the hinge formation will start, still the section, still the beam can resist the more load. The elastic theory underestimates the load carrying capacity of the structure. So from so what the design we are taking, that is by the elastic theory. All design that is based on the elastic theory. But if we design on the elastic theory, so that underestimate the load carrying capacity of the structure. So for indeterminate structure, see, this underestimation is higher. So for determinate structure, so this is your underestimate the load carrying capacity of the structure. And if you consider the indeterminate structure, so that case the underestimation is your more than what is for the determinate structure. And that term, the factor of safety, does not give the correct idea about the load carrying capacity of the structure. In elastic design, you are considering the factor of safety, but this is not giving the correct idea for load carrying capacity of the structure. Hence, a new theory, a plastic theory, has been developed. What you are designing by considering the elastic theory, so that is you are underestimate the load carrying capacity of the structure. And if you take the indeterminate structure, so that case the underestimation is more than what is for the determinate structure. So that case, so this theory will not give the correct result, and CF2. Hence, the plastic theory is your developed. That is your by considering this negative side of the elastic theory. What is plastic theory? In plastic theory gives the correct idea about the load carrying capacity of the structure. And this theory is based on the concept that the structure will carry load till the plastic hinges are formed at the sufficient points to cause collapse of the structures. In this theory, the plastic hinge will be formed at the sufficient points to cause the collapse of the structure in the plastic theory. However, to make the theory simple, strain hardening of the metal is neglected, which means the load carrying capacity of structure is actually a little more than what plastic theory predicts. So how to make the theory simple? Strain hardening of the metal is neglected, which means the load carrying capacity of the structure is actually a little more than the plastic theory predicts. What is your plastic hinge? It is a section at which all the fibers yield. So this is the section at which all the fibers yield, and hence any further load rotation takes place at the section without resisting any additional moment. This is your plastic hinge. So after yielding all the section, so the hinge formation takes place, the rotation of the section takes place without resisting any additional moment. That is called the plastic hinge. And what is plastic moment capacity? The plastic moment capacity of a section may be defined as the moment which makes all the fibers of the section to yield and thereby form a plastic hinge. So in the case of plastic moment, what is your plastic moment capacity? When at any section all fibers yield, so the hinge formation takes place. So at that moment, what is the plastic moment? That you have to consider the plastic moment capacity of the section. Or that is at the formation of plastic hinge, what is the moment carrying capacity of the structure? That is called the plastic moment capacity. You are clear? The plastic hinge means, so when all fibers at a section are yielded, so the hinge formation takes place, the rotation takes place, and that rotation, that hinge is called the plastic hinge. That is and that is due to without resisting any additional moment. And what is plastic moment capacity? After formation of plastic hinge, what is the moment carrying capacity of the structure? And that capacity is called the plastic moment capacity. These are the assumptions in plastic theory. You have to remember the stress-strain relation is idealized into two straight lines. Strain hardening effect is neglected. So these are the assumptions. The stress-strain diagram is your two straight line. This one. This is the in plastic theory. This is the stress-strain diagram. So this is one straight line and this is another straight line. But in elastic theory, This is in elastic theory, this is the stress strain diagram. This is stress strain diagram in elastic theory, but this is in plastic theory. This is two straight line. The stress strain diagram is a two straight line. This is and this is. And here you are neglecting the strain hardening effect. Strain hardening effect is neglected in the case of plastic theory. The section before bending remains plane even after bending. That is, the shear deformation is neglected. So you know that is in elastic theory. The section before bending also remains plane even after bending. Here also in plastic theory, this is your valid. The section before bending remains plane even after bending, and the shear deformation is your neglected. And the third assumption, the relationship between the compressive stress and compressive strain is the same as between tensile stress and tensile strain. So what is the compressive stress and compressive strain? The relationship, and that is same as between the tensile stress and tensile strain. Then the fourth assumption, whenever a fully plastic moment is attained at any cross section, a plastic hinge is formed which can undergo rotation of any magnitude, but bending moment remains constant at fully plastic bed. Then the fifth one is your effect of axial load and shear on fully plastic moment capacity of the section is neglected. At the time of fully plastic moment capacity, here the effect of axial load and the shear, so this is your neglected. Then the deflection in the structure are small. So in the plastic theory, so this is the assumption that deflection in the structure are considered small. Then what is shape factor? To find out the shape factor of the different section. So what is shape factor? So within elastic limit, the bending moment M has a relation with the bending stress F. You know that is in the elastic theory. What is the relation between the bending moment and bending stress? That is, you know, in mechanics of solid. That is in theory of pure bending. What is the relation between the bending moment and the bending stress? So bending moment is equal to the bending stress into the section modulus. Bending stress into section modulus. You know, in the theory of pure bending, so the bending moment is equal to the bending stress into the section modulus. Z is the modulus of section or section modulus. So defining the moment causing extreme fiber to yield as yield moment. You know that is when the extreme fiber is yielded, so that is called the yielding moment, My. We can write the yielding moment is equal to the bending stress, the yield stress into the section modulus. Yield stress into the section modulus. Fy, yield stress into the section modulus. If plastic moment capacity of section is MP, plastic modulus of section Zp is defined as the ratio of plastic moment capacity to yield stress. So this is the plastic modulus of section Zp. You can denote this is in elastic theory, the modulus of section. The bending moment is equal to yield moment is equal to yield stress into the section modulus. But in the case of plastic theory, you can denote the section modulus, that is your plastic section modulus or plastic modulus of section, and it is defined as the plastic moment capacity to yield stress, MP by Fy. So this case, the section modulus is equal to yielding bending moment by yield stress. But in this case, the plastic section modulus is equal to the plastic moment by the yield stress, MP by Fy. So MP is equal to Zp into Fy. The shape factor. So what is the definition of shape factor? The shape factor may be defined as the ratio of plastic moment capacity to yield moment. So you know that is in the case of plastic theory, this is the plastic moment capacity MP, Zp into Fy. But in the case of elastic theory, you know, so this is the yield moment, My is equal to Fy into Z. Z is your section modulus and Zp is your plastic section modulus. So what is the shape factor? Shape factor is equal to it is the ratio of the plastic moment to the yield moment. You know, plastic moment is equal to Zp into Fy, and the yield moment is equal to Fy into Z. So here Fy and Fy cancel each other, and the shape factor is equal to the plastic section modulus divided by the section modulus. You can say the ratio of the plastic moment to yield moment is known as the shape factor, or also you can say the plastic section modulus to section modulus is called the shape factor. The shape factor is always greater than unit. the ratio is always greater than unit. This is the plastic section modulus, and this is the section modulus, and the ratio is always greater than unit. So let us take one rectangular section and find out what is the shape factor of the rectangular section. So this is your rectangular section, and the width of the rectangular section is your B, and depth of the rectangular section is your D. And this is your compression side above this axis, neutral axis compression, and this is your tension. You know, in simply supported beam, above neutral axis, the zone is your under compression, and below neutral axis, the zone is your under tension. So this is the yield stress in compression side, and this is the yield stress in tension side. This is your stress diagram. This is corresponding to the yield moment, and this is your corresponding to after yielding the all section, all fibers. So this is the stress diagram. This is in compression side. The yield stress is your constant in compression side, and also constant in the tension side. But you see in the elastic theory, after yielding the extreme fiber, outermost fiber, this is the yield stress. Still, the inner fiber is your under stress. But in plastic theory, what you have to consider, so the inner fiber also still resists the more load. That's why, so this is the stress diagram in the plastic theory. So here the Fy is your constant throughout the section, compression and tension. And this is the compressive force Fc, and this is the tensile force Ft. So here A1 and A2, the area of the compression side is your A1, and area of tension side is your A2. And this is the yield stress Fy. And this is the D by 4, the central axis from the neutral axis. This is also D by 4. So here you see, you know the yield moment is equal to My into Fy into Z. Bending stress into the section modulus. Bending stress into section modulus. This is your Fy. You know that is the in rectangular section. What is the section modulus? The section modulus is equal to 1 by 6 BD square. Already you know this is how to find out the section modulus. So this is your moment of inertia divided by the most distant point from the neutral axis. Using that formula, you can find out what is the section modulus for rectangular section. This is 1 by 6 BD square. But you know in the plastic moment, so A1 is your under compression area, and A2 is your under area under tension. And the compression force is equal to tension force. Compression force is equal to tension force. So, but the compression force is equal to Fy into A1. This is the yield stress into the area A1 is equal to the compressive force. Similarly, this is the yield stress into area A2 is equal to the tensile force Ft. So, Fy into Ft. So, here you see the A1 is equal to A2 is equal to A by 2. The total area of the rectangular section is your A. So A1 is equal to A2 is equal to A divided by 2, where A is the total area. Thus, the plastic neutral axis divide the area into two equal halves. So in the case of plastic theory, the neutral axis divide the area into two equal halves. So A1 is equal to A2 is equal to A by 2. Hence in rectangular section, it is at the mid depth. So the neutral axis passes at the mid depth in the case of rectangular section. Also in the elastic theory, this is also passing through the mid section of the section. This is your neutral axis. Here in elastic theory, this is the stress diagram, compression and tension side. And in plastic theory, this is the stress diagram. The plastic moment capacity is the moment of resistance where the yield stress is Fy at all the fibers. You have to find out the plastic moment capacity. So plastic moment capacity is equal to Fc into Y1 plus Ft into Y2. So this you have to take the bending moment from the neutral axis. So Fc into Y1. This is your Y1 distance plus Ft into Y2. Fc into Y1 plus Ft into Y2. But you know the total compressive force is equal to Fy into A1 into Y1 plus the total tensile force is equal to Fy into A2 into Y2. Fy A1 Y1 plus Fy A2 Y2. So here you take the common A1 A2 is equal to A by 2. A1 is equal to A2 is equal to A by 2. So here you take Fy into A2 common. So Y1 plus Y2. So Y1 is this distance. Y1 is equal to D by 4 and Y2 is equal to D by 4. You have to put here D by 4 plus D by 4. Then after simplifying this one, so you'll get the plastic moment is equal to Fy into Bd square by 4. Then you have to find out what is the shape factor. The shape factor is equal to the plastic moment divided by the yield moment. So plastic moment, you know, this is your Fy into Bd square by 4, and you know the yield moment. This is your Fy into 1 by 6 Bd square. Fy into 1 by 6 Bd square. Fy Bd square by 4 and Fy Bd square by 6. So here Fy cancel each other, and Bd square after simplifying this one, so you'll get the shape factor is equal to 1.5. So here similar way you can find out what is the shape factor of the triangular section and also in circular section. So the shape factor of the rectangular section is 1.5. This is rectangular section and the shape factor is equal to 1.5. Similar way, you can find out what is the shape factor of the circular section and what is the shape factor of the triangular section. The shape factor for circular section is 1.698, and for shape factor for triangular section is 2.343. This is the circular section, and the radius of the circular section is R, and the diameter of the circular section is capital D. In this case, the shape factor is equal to 1.698. Similarly, in triangular section, this one. So here the width of the triangle and h is the height of the triangle. So here you can find out what is the shape factor. So here this is your shape factor is equal to 2.343. So this is the assignment for you. So you find out what is the shape factor of the circular section and what is the shape factor of the triangular section. Then what is collapse load? A structure is said to have collapsed if the entire structure or part of the structure starts undergoing unlimited deformation. This happens when the number of independent static equilibrium equations available is more than the number of reaction components. So the state at which this condition develops is said to be collapse mechanism. And the load carried at this stage is called the collapse load. So at the stage of the collapse mechanism, what is the load carrying capacity of the structure? So that is called the collapse load. And the collapse mechanism forms when the part of the structure or entire structure starts undergoing unlimited deformation. That is, the yielding takes place and the plastic hinge formation start, and then the collapse mechanism will be formed. And the other stage, so what is the load carrying capacity of the structure? That is called the collapse load. The collapse load is also called the ultimate load carrying capacity of the structure. And also you can say that determine the collapse load of a structure is called the plastic analysis. So in plastic analysis, you have to find out the collapse load of the structure. Normally, structures are permitted to carry only a fraction of collapse load, and this load carrying capacity is called the working load. Normally, all structures are permitted to carry only a fraction of the collapse load, and this load is called the working load. So the collapse load is equal to the load factor into working load. Collapse load is equal to load factor into working load. So the load factor is equal to collapse load by working load. You have to remember this definition. Load factor is equal to collapse load by working load, and factor of safety is equal to yield stress by working stress. Then what are the basic theorem for finding collapse load? So there are three theorems. One is your static theorem, then kinematic theorem, then uniqueness theorem. These are the three theorems. So for finding the collapse load. So what is static theorem? State for a given structure and loading, if there exists any distribution of bending moment throughout the structure, which is both safe. This is your safe. The set of loads W. The value of W must be less than equal to collapse load WC. So in the case of static theorem, the W is less than and equal to WC. The value of W must be less than equal to collapse load. In the term statically adducible means the bending moment diagram satisfies the static equilibrium conditions. In the case of statically adducible, the bending moment diagram satisfies the static equilibrium conditions. The term shape means shape. At no point bending moment is more than plastic moment capacity of the section. So this theory is also called lower bound theorem. The static theorem is also called lower bound theorem. So here you have to remember. So the W is less than and equal to the collapse load WC. And in kinematic theorem, W is greater than or equal to WC. This theorem states for a given structure subject to set of loads W, the value of W found to correspond to any assumed mechanism must be either greater or equal to the collapse load. So, in this case, W is greater than or equal to WC. So, this is also called the upper bound theorem. Kinematic theorem is called the upper bound theorem, and the static theorem is called the lower bound theorem. Then what is uniqueness theorem? The static and kinematic theorem combine to form a theorem which gives unique value for collapse load. This theorem is called the uniqueness theorem. Unique value of the collapse load, that is the combination of the static and kinematic theorem, and give the unique value of the collapse load, and this is called the uniqueness theorem. So if for a given structure and loading, at least one shape and statically adversarial bending moment distribution, the bending moment is equal to the fully plastic moment at enough cross section to cause failure of structure due to the unlimited rotation at plastic hinge. The corresponding load will equal to the collapse load in the case of uniqueness theorem. So these are the methods of plastic analysis. So one is your statical method and another one is your kinematic method. So based on the uniqueness theorem, there are two methods of plastic analysis, statical and kinematic method. So both the methods are based on the important assumptions. That is, once a plastic hinge is formed, rotation takes place freely without any change in the moment, acting in the section. This may be represented by moment curvature relation. This is the moment curvature relation. This is the plastic moment, so this remains constant without increasing the plastic moment capacity. Here you see the moment is increases when the curvature is increases, the moment is increases. And here this is the remain constant, the plastic moment. After increasing the curvature, the plastic moment is remain constant here. So this is the statical method. This method is suitable for the analysis of structure for which the shape of the bending moment diagram is easily known. This method consists of drawing statically adversarial bending moment diagram and equating this bending moment at sufficient number of points to plastic moment so that a collapse mechanism forms. The bending moment will not exceed the plastic moment capacity of the section at any point. So in this case, the bending moment will not exceed the plastic moment capacity of the section at any point in the case of statical method. But in kinematic method, this method starts with the assumed collapse mechanism. This method you can start from the assumed collapse mechanism. After collapse mechanism is formed, there can be no change of curvature at any cross section except where plastic hinges are formed. Hence, if a virtual displacement is given to the structure, at that point you have to give the virtual displacement. Just after collapse mechanism is formed, the internal work is done only at plastic hinge where plastic moment is acting. So you have to find out the internal work done due to the plastic moment that is found at the plastic hinge. So in this case, you have to take internal work done by plastic moment at plastic hinge is equal to external work done by load. So using this formula, you can find out the collapse load in the case of kinematic method. All possible mechanisms can be investigated and the one giving least value may be considered as the real collapse load. So which one is you are giving the minimum value, least value, so that you have to, in which mechanism you will get the least value, so that you have to consider as the real collapse load of the structure. So this method is also known as mechanism method or virtual work method. Using these two methods, you can find out what is the collapse load of a structure. So now you are clear